So you've survived test one. You'll get your test results back this weekend. Um, Listen, I noticed that some of you weren't aware that when I grade your papers, your special homework, that is available for you to download and look at. More than just the score is available. So does everybody know how to access that in Blackboard? I see some people nodding yes, that's good. You can always download your graded work. I've marked it up just as if it was a hard copy that you turned in and uploaded the marked up version, the PDF, in the student, feedback, the feedback to student. So, just FYI, of course, your graded work has always been there, waiting for you to take a look at more than just the score. So that was a surprise to me that some very good student actually said, I didn't know I could download my graded work, but of course it's there. It's there in Blackboard. So be sure and do that. We may have a couple of visitors tonight from the regular class. A couple of people weren't feeling well and they may join us this evening. I hope that's the case. All right. Any questions before we get started with tonight's lecture? All right, we're going to start with a review tonight since it's been several days since we went over our new definitions. Of course, we're starting proofwriting, and proofwriting depends upon a couple of important things. The one thing that it's going to hinge on is your understanding the logic, the pure logic that we have studied so diligently from chapter 2. And then the other thing it's going to depend on is these new definitions, because everything that we do will be according to definitions so that we can all agree on what we're talking about. So let me go ahead and pin the notes here. So here's a quickie review of our definitions. That's what we're going to do. We're going to review the definitions. We're going to learn one new definition, perfect square. And then we're going to talk about, like, the big deal is understanding the difference between proving a universal statement and proving an existential statement. These types of proofs are completely different because to prove an existential statement, as you learned when we played Tarski games, all you got to do is come up with an example, like come up with an example of an object X and an object Y that are like same color and same shape or whatever the predicate says, right? But when we're proving a universal statement, we can't prove a universal statement by example. It has to be proven for all objects in the domain. So we'll be looking at several examples to kind of illustrate the difference between existential proofs and universal proofs. And then we're going to talk about disproving a statement. We know that a statement and its negation have opposite truth values, right? So if we are disproving a statement, we're actually proving its negation, right? So we'll talk about that. All right, so just to quickly review, an integer n is even if n equals 2k for some integer k. An integer n is odd if n equals 2k plus 1, where k is in z. That's just another way of saying for some integer k. I'm trying to write things several different ways so that you can understand there's more than one way to write these ideas. An integer n greater than or equal to 2 is prime if its only positive divisors are 1 and in itself. And then, and sometimes we get a little lazy about saying positive. Sometimes we just say it's only divisors or 1 and in itself. That's fine. We all know what we're talking about there. That's one of the few times when we can kind of shirk complete rigorousness. And then an integer n greater than or equal to 2 is composite if there exist integers a and b such that n is the product a, b, where 1 is less than a and 1 is less than b. And we looked at examples of these kinds of numbers last time, so you can review those notes. Here's our new definition. And this is the first time that I'm going to give you a definition, and then I'm going to leave it to you to actually work with the definition. We'll have plenty of office hours. If you have difficulty, the special homework 5 is already posted, due next Wednesday. And the last problem in that homework deals with this definition. An integer x is a perfect square if x is equal to n squared for some integer n greater than or equal to 0. So that's our new definition tonight. And again, part of my job is to teach you how to learn to read and write mathematics. So I'm going to let you read this definition and then try to write using the definition. Before we do that, though, let's just go through a couple of perfect squares. What is the smallest perfect square according to this definition? Anybody? You can chat in or you can mic in.
1.
That's almost the smallest because 1 is certainly a perfect square. It's equal to 1 squared, but there is a perfect square that's even smaller than 1.
0.
0, because 0 equals 0 squared. N is allowed to equal 0. So 0, 1. What's the next perfect square after 1 if we're counting up? Like we're going 0 squared is 0. Okay, 1 squared is 1. What's the next one?
2 squared.
2 squared, and that's 4. And then the next one, of course, would be 9, then 16, 25, 36, et cetera, et cetera. Get the drift? Okay, good. All right, so let's go ahead now and talk about proving statements. Because that's, honestly, that's the deal. We want to be able to prove a statement. So there is a big difference. So it's worth writing this down. There is a big difference between proving an existential statement where we're claiming something exists with some property and a universal statement where we're trying to prove that some property is universally true for all objects in a domain. There's a big difference, okay? So let's go ahead now and look at some facts. Fact 1. To prove an existential statement, and let's review the form of an existential statement. So to prove an existential statement of the form, I guess in its simplest formalization, it would look like this. There exists an X in D, some domain, such that P of X, some predicate for X is true, some property holds. Or as we have seen, we might have a couple of objects that exist. It might be something like there exists an X in D and there exists a Y in some set, say F, such that some property P of XY holds. Okay, we've seen these types of statements. So to prove an existential statement of this form, we must, well, what do we need to do? We must find an example of an object X. Or if it's the case of two objects, we're going to find an X and a Y. And we have to do a couple of things. One, we have to verify the X that we pick lives in the proper domain. So we verify X is in the domain D. And if it's the case of two objects, we're going to show X is in D and Y is in F, for example. And then 2, we're going to verify the predicate P of X holds, whatever that is. And we'll look at examples tonight. In the case of an example with 2 objects, it would be P of XY, okay? So there are two things we have to do. And when we are trying to prove an existential statement, we usually have to crack out some scrap paper and just poke around and try to find an example. So scrap work is often needed. Just an FYI. Now, so that's to prove an existential statement. What if we're trying to prove a universal statement? Let's look at what happens in that case. To prove a universal statement, of the form, let's just review the form of a universal statement, for all x in D, something is true, say P of x, okay? Or if it's a couple of objects, it might be like for all x in D, and for all y in F, some predicate P of x, y holds, okay? So whatever, the situation is, we cannot use an example. We can't prove it for just one x. That wouldn't be a universal proof. We must use well, we have a list here. We have to use variables that represent the objects. Just make sure my mic is off here. The object or the objects, variable or variables. Definitions that are in play. We're going to be using our definitions. And we'll be using whichever ones appear in the statement. So that's what I mean by in play. We're going to use algebra, equations, and inequalities to make our points. We're going to also, remember, use things that we may assume without proof. We had a couple of things that we may assume without proofs. Let's just review that. One of the things that we can use without proof is the idea that the integers are closed under the operations of addition, subtraction, and multiplication. We talked about that at some length in day 9, and I encourage you to go back and listen to that lecture if you need to review. But closure means, hey, if you've got two integers and you add them together, the result, that sum, is an integer. Same with differences. If you subtract an integer from an integer, the result is an integer. Same with multiplication. Product of two integers is always an integer. These are called the closure properties of Z, the integers, under those operations. But the integers are not closed under division, right? 1 divided by 2 is not an integer, okay? The other thing that we may assume without proof was called the zero product property. And the way that it was phrased was as a universal if-then. For all real numbers, x and y, if x times y equals 0, then x equals 0 or y equals 0. And one of the things I asked you to do later in our day 9 lecture was to write the contrapositive formulation of that zero product property. And I hope that you did do that. The reason I asked you to look at the contrapositive is, of course, it's logically equivalent to the original if-then, and it is the way we generally apply the zero product property. So go back and look at day 9 notes and do later, and write the zero product property in its contrapositive formulation if you haven't already done that. Then finally, of course, we show that P of x, or if it's got a couple of variables, P of x and y holds, okay? So it's a completely different game if we're trying to prove a universal statement versus an existential statement. And we're going to look at numerous examples of both tonight so that you can kind of get comfortable with this idea of what's required to do a proof, to write a proof of a quantified statement. All right, let's start with existential proofs. They're the easiest ones because all we got to do is cook up an example. All right, so we're going to start with two existential proofs. And I have stopped using red here during our lecture. It doesn't seem to show up that well on camera for some reason, but the notes have some red in them, so it doesn't really matter. Just FYI. All right, example one. Here we go. Let's prove there exists a prime number, P. I'm going to go ahead and name it P, such that 2 to the P whole thing minus 3 is not prime. 2 raised to the P minus 3 is not prime. So we're going to be hunting for a prime, and then we're going to keep plugging in different primes until we find one that does this job of making this expression 2 to the P minus 3 not a prime. Notice I didn't say composite here because there are other reasons why a number might fail to be prime. It might not be even big enough to be classified as prime or composite, right? The smallest prime or composite number is 2. So here's some scrap work. I just want to kind of show you how that can happen. And here's my big advice, folks. Keep it simple. Keep it small. When you're looking for a prime that has a certain property, start small. I should say start small there. You're not going to start with like P equals 37. Okay, that is a prime, right? But the minute you try to plug in 2 to the 37 in your calculator is going to start giving you all kinds of weird stuff. You know, it's going to be hard to see what's going on. So let's just keep it simple, keep it small. What is the smallest prime we might try out? Anybody remember what the smallest prime is?
Two.
Yes, our only even prime and the smallest prime, folks, is 2. Okay, so let's try P equals 2. All right, it's going to be real easy to claim it's prime. Its only divisors are 1 and 2, so that's not a problem. But let's check this predicate. 2 raised to the P minus 3 is the quantity that we want to look at, right? So we're looking at 2 squared minus 3. Of course, that's 4 minus 3, and that is 1. Well, 1 is not prime because it's not big enough to be a prime. So yay, we quickly found an example of a prime P that satisfies the predicate. First one we tried. Doesn't usually work out that way, but it did for this first example. Now, listen, I don't often say to read the book, like really definitely to read the book. But if there's only one section in this entire ebook that you actually sit and read, you're going to want to read section 4.2. One of the things you're going to learn in section 4.2 is how to write a proper proof. And the first thing that you need to do when you're starting a proof is let your reader know, hey, the proof is starting right now. So this is what I like to put as my sequence of symbols to indicate the proof starts here. You don't have to use this. You could write proof with a colon or something else, but just make sure that you decide you have a sequence of symbols that indicates the proof starts here. Now, we've done the scrap work. We found a prime that works. How do we introduce that to the reader? Like, how do we even start this conversation? Well, one of the nice words that I like to use is the word consider. especially when I'm proving an existential statement. And the reason I like this word consider is because it's like, hey, I've thought about this. I've thought about this, and now I want you to consider my thoughts. Okay. So it's a very nice way to start this out. Consider P equals 2. Now, there are two things we have to do. We have to verify that 2 is in the domain. We're going to have to verify it's prime. And then we're going to have to verify that 2 works to make the predicate 2 to the p minus 3 is not prime true. We're going to do both of those. So notice, we're just going to write complete sentences. It's almost like you're talking to somebody. 2 is primed. We just have to say it because its only divisors are 1 and 2. I'm not even bothering to say positive divisors. We can kind of get away with that much. Okay. And now, here's the gravy. We really want to verify that 2 works. So we just do the algebra. We've already done it in our scrap work. It's easy to do. 2 to the p minus 3 is equal to 2 squared minus 3. Show the work. It's 4 minus 3 equals 1, which is not prime. And now we're going to verify that 1 is not prime. Why? Because 1 is not even greater than or equal to 2. It doesn't even qualify. And it's that simple, folks. We've done 2 things. Well, really 3. We've introduced our suggestion for the object. We verified that the object lives in the right domain. Here it needed to be prime. And we verified that the predicate holds for this object that we chose. The predicate was this property, that 2 to the p minus 3 is not prime. Questions? All right, so let's do another one. Kind of on a roll here. Let's do another existential proof. They're kind of fun, actually, because it's like a little hunt. You know, we're on the hunt here. Let's prove there exists a prime number p such that 2 to the p minus 3 is composite. I'm making a point here. The first one was that 2 to the p minus 3 is not prime. Saying that 2 to the p minus 3 is composite is saying a little bit more. It's not only saying it's not prime, it's saying it's big enough to even qualify for being composite, right? All right, so we're going to be looking for a prime. We're going to do some scrap work. We already know that p equals 2 is not going to work, right? It did not make a composite. It made the number 1, right? So it would make sense now. Let's just keep it small. What's the next prime up from p equals 2? Like, what would be a reasonable next prime to take a shot at?
3.
Yep, let's try p equals 3. I really appreciate your involvement here, your participation. Let's try p equals 3. Okay, here we go. So 2 to the p minus 3 is now 2 cubed minus 3. That's 8 minus 3, and that's 5. Is 5 composite?
No.
No, it's so okay, fine. That's okay. We're on the hunt here. 3 did not work because 5 is not composite. It's prime. Let's try the next prime. P equals 5. Okay. So 2 to the p minus, you can see where this is going. 2 to the p minus 3 is 2 to the 5th minus 3, of course. And that's 32 minus 3, and that's 29. Is 29 composite?
No.
Nope. So we're like, okay, don't lose hope, right? One's gonna pop up. Okay, let's try p equals, what's the next prime?
7.
Yeah, let's try 7. All right, now, so I'll just go right to 2 to the 7th minus 3. Anybody know what 2 to the 7th is? Y'all should know the powers of 2, right? You're computer science people. You should know the powers of 2 up to at least 2 to the 12th.
128.
128, nicely done. Minus 3. Now we're looking at a grand total of 125. Is that composite?
Yes.
Yes,
Yeah.
it is. Give me a factorization because we're going to have to prove it's composite. How are we going to factor that baby to show it's composite?
5.
5 times like 25 will work, right? Good. It's definitely composite. Yay. Okay, so we found one. All right. So we're feeling very good about ourselves. Now let's practice writing it up. Remember, there are 2 things that we're going to have to do. We're going to verify that our choice of the object lives in the right domain. We're going to verify 7 really is prime. Then we're going to verify that this predicate holds. We've already got the work done here. We're simply going to rewrite it into the actual proof. All right. Let's do this. So example 2, here's our proof. So consider p equals 7, or you can say let p equals 7. If you don't want to say consider, that's fine. You could say let. You could even say assume, but usually we use assume when we have a variable. All right, notice 1, 7 is prime. We just say it, right? Because its only divisors are 1 and 7. And this is nice because it helps us practice the definitions. And now 2 to the 7th minus 3 is 128 minus 3, which is 125, which is 5 times 25. Now we are not quite done. Let's just review the definition of composite. I'm going to put it up here where everybody can look at it. There's more to the definition of composite than n equals a times b. Like this is the first part. N equals a times b. We got that. 2 to the 7th minus 3 is a times b. But we have to say a few things more, right? We have to mention that a and b are integers. We just have to say it, that 5 and 25 are integers. Also, we're going to have to mention that 1 is less than 5 and 1 is less than 25. There's nothing to prove here except just to say these things. By saying these things, we are saying that we're addressing every part of the definition of composite, and that's important. So here we go. So notice 5 is an integer, it's NZ, and 25 is NZ, and 1 is less than 5, and 1 is less than 25. So 2 to the 7th minus 3 is composite. So that's part of what we learn to do. We learn to be what's called rigorous. And sometimes it's going to feel like rigor mortis. But what it is we are dealing with a definition that has various parts. And in order to really nail it, we have to address every part of the definition. Questions? So I am going to give you a couple of do later problems that will be good problems, you know, when you're feeling like you need some more practice. Okay, a lot of times that's what I hear students say, gosh, you know, I need some more practice. Of course, one of the things you learned in homework 1 was that the book has lots of examples of problems, often with solutions included that you can practice on. We are in section 4.1 and 4.2 tonight, but here are a couple of do-laters that are specifically tailored for you by me. Find a prime P such that 2 raised to the quantity P minus 1, whole thing minus 1 is prime. And just to show you, kind of to make a point that it's not universally true, let's, for 2, find a prime P such that 2 to the P minus 1, whole thing minus 1 is composite. You can find examples of primes that make each of these true. In other words, we wouldn't be able to prove for all primes P that 2 raised to the P minus 1 is prime or composite, because for some primes P, this quantity will be prime, and for other primes P, this quantity will be composite. Okay. So now let's get to proving universal statements. These are generally going to be a little bit more involved, and we have some important steps that we're going to take to help ourselves with our proving of universal statements. We cannot prove these by example. Okay, we cannot do that. But what we can do is remember some facts about universal statements. Let's go to the gallery. We learned some things about universal statements, if-then statements. We learned that every universal statement is an if-then statement. There's a way to write it as an if-then. And we also learned that every if-then statement is universally quantified. Okay. So one of the great things that we're going to use that we've learned from chapter 2 is that when we are trying to prove if P then Q, we remember something really nice. What is the truth value of if P then Q when the hypothesis P is false? I'll ask that again. If we know that the hypothesis P is false, what is the truth value of if P then Q?
True.
It's true by false hypothesis. Remember the truth table for if P then Q? It's only false if the hypothesis P was true and the conclusion Q was false, right? And that actually really matters, because what it means for us is we don't have to worry about what happens or doesn't happen when we're trying to prove if P then Q in the case that P is false. There's no work to do there. If P is false, the if then is true by false hypothesis. It means we only have work to do when the hypothesis P is actually true. And that's going to make our life a lot easier. Here's an example, and we're going to walk through some things before we actually attack it. But let me just show you an example. Prove the sum of 2 even integers is even. Super simple statement, but we can't prove it by example. Now, there are numerous proof methods that we're going to learn, but we are going to start the way that it is always started when one learns to write proofs. We will use the direct proof method. Direct proof. What is direct proof? It means, hey, we're going to try to prove an if-then. Do you see that this is a universal statement? It's not explicit. It's implicitly universally quantified. We don't see the word all or every. or each, but it's implied that we're talking about the sum of any two even integers. Okay. Remember when we first talked about universal statements and implicit versus explicit, our example, I think, was all fish swim, right? That was like our first example of a universal statement. All fish swim, or every fish swims. But we could write that implicitly, fish swim, and we understood that that meant all fish swim. Well, it's the same here, folks. This is implicitly universally quantified. The other thing that we learned is that this can be expressed as an if-then statement. So I'm going to teach you two things, and we're going to call them, I know it's corny, good step 1 and good step 2, because these are really going to help you when you're trying to learn how to write a universal proof. Good step 1, write the universal statement as an if-then, as a conditional. Write it as a conditional. And I'll show you the reason for that, i.e., as an if-then statement. Introducing variables to represent the objects. We're going to introduce variables. Why? Well, if we want to talk about these two even numbers, they need to have names. We're going to name them so that we can write equations about them. Okay. So without a name, which is a variable, we can't say a lot. So that's the first step, is we're going to write these as if-then statements. And then there's good step 2. Why are we writing this as an if-then anyway? Well, because we want to identify the hypothesis. That's the next thing that we do. Once we've written it as an if-then, we can identify the hypothesis. This is what we will assume. I'll put that in capitals. This is what we will assume. That's why it's called our hypothesis. And then we're going to identify the conclusion. Why? Because that's what we wish to prove. And we're not going to get involved yet with the definitions. We're just going to try to write this statement. The sum of two even integers is even, using some variables. So don't get involved in the definitions yet. All right, so here we go. The reason we're going to write it as an if-then is because we want to get our eyeballs on the hypothesis and the conclusion. All right, here we go. So this is our example 3. I'll just write it again so I can move this other piece of paper. Prove the sum of two even integers is even. And you might be tempted, right, to just prove this by example. You might be tempted to say, oh, I'll just take my two favorite even integers, like maybe I'll let one of them be 4 and the other one be 10. When I add those up, 4 plus 10 is 14, and that's even. Done. Nope, we can't prove it using an example. It's not an existential statement. It has to be proven for all even integers. So now let's go ahead and do good step 1. Let's write it as an if-then and introduce variables to represent these even integers. So we could say if A, or you could call them X and Y, I'll just use A and B. If A and B are even integers, then what do we want to show? What is the conclusion?
That it's even?
Yeah, good. And what is it specifically?
The integers.
The assumption is that A and B are even integers. Let's read the statement again.
The
Prove
sum.
the sum.
Yeah.
Right. We want to say something smart about the sum, and we write the sum as A plus B. And see, that's another big advantage of naming these even integers, because then we can write an expression for their sum. See where I'm going with this, everybody? By introducing variables to name these even integers, then we can start writing expressions for their sum, or if it was about their product, we could say A times B, but this is sum. Oh, sorry. What did I want to write here? Then A plus B is what? What did I want to put here?
Even.
Even, thank you. Sometimes when I say a word and I'm writing, I write what I, there we go, is even. All right, that's what we want. And now good step 2, I'll just call it GS2. Hey, identify the hypothesis. That's the if part, right? The hypothesis is that A and B are even. This is what we're going to assume, folks. This is going to be like money in the bank. It's going to be like walking up to the math ATM and we're going to get cash out when we actually apply the definition of even to A and B. I'll show you what I mean. And then we see the conclusion. That's what we wish to prove. All right. Writing proofs is not hard. There's actually a method to this madness. And this is the first kind of thing to learn is if we write our statements as if-thens, we can get our eyes on the hypothesis. Ooh, that's what we get to assume. We get our eyeballs on the conclusion. Hey, that's what we need to show. All right, here we go. Our first universal proof. So we assume the hypothesis. So we can just write and we can use the names that we picked. I picked A and B. You could have used X and Y, M and N. I like A and B. Assume A and B are even integers. Okay, that's our hypothesis. We got to have something to work with, right? We can't just pull this out of thin air. We got to know something. Now, everybody in this room has taken COSC 236, right? So you know a little bit about coding. And you know that when you write code, not all of it compiles because there's a symbol that you can use in Java that indicates to the compiler, hey, what I'm writing after this symbol isn't part of the code, it's documentation, right? You write documentation so that you know yourself later what the module is supposed to do if you're writing a module, and the next poor fool that's trying to use your code knows what the module or what the code is supposed to do. It's called documentation, right? So we're going to start using a symbol or a set of symbols that's going to indicate to the reader and to ourselves, hey, this next part isn't really part of the proof, but it's information, it's documentation. And what they are called is thinking notes. We're going to use what I call thinking notes to write what is our wish. Literally, our wish is to prove that the conclusion follows, okay? So the documentation symbol is just square brackets. If you open a square bracket, I know that I will never downgrade you for whatever you write inside square brackets. It doesn't compile, okay? It's not part of the proof. But it's important to write these because if you don't know what you're trying to do, if you don't know what you wish to prove, then how in the world are you going to actually prove it? So we wish to show that the conclusion follows. In this case, we wish to show A plus B is even. All right, so we'll just put that in square brackets, and that just lets us know, hey, we're going to be looking at A plus B. We're going to be trying to show that it is even. All right? All right, great. Now, this is huge. Just having our hypothesis written down and knowing what we're going to try to do written down is like a lot of the battle. In fact, there's some WebAssign problems where that's all you're asked to do. You're just asked to write the hypothesis, what you would assume, and write down what it is you would be trying to show. Okay? All right, so once we've got that done, where do we go from here? What would be the next step? The next step is, do you hear that? Do you hear that? Listen. Use the definition. All right, it's better closer to Halloween. Use the definition. I'm telling you, when you're stuck, when you're trying to write a proof and you are stuck, that's the voice you want to listen to. Because if you use the definition, you're going to get equations. And that's like money in your math wallet that we're going to pay out later to write the proof. So let's use the definitions. What is the definition that's in play here? Look at our hypothesis. What definition are we going to break out here?
Is it the one with like that integers remain unchanged through like addition and yeah.
You know what? We will use the property called the closure property, right? But that's not definition. The definition in play here is that A and B are even. All right. They're not prime in this particular problem. They're even. We're going to use the definition of even. Okay. So usually you can just read the hypothesis and you'll see a term that is a defined term. Here it's even. But you're right. We're definitely going to use that property, that closure property too. All right, so here we go. We're going to use the definition. And then we tell the reader that's what we're doing. By the definition of even, we know. Here we go. Well, A is even. So let's just go ahead. A equals 2 times K, where K is in the integers, right? K is in Z. But B is also even. So we can write an equation for B. Now let me ask you this, and this is important. We've already used K for A. A equals 2K. Do you think that it would be wise to use the same letter K when we apply the definition of even to B? Nope.
No.
Yeah, we got to pick a different letter. So J is good. Okay. They're right next to each other. Hey, listen, what do you not want to use for variables? You don't want to use I because I equals square root of -1, right? It's already kind of spoken for. You don't want to use O for obvious reasons. O looks like a 0. And you don't want to use an L that's just like a stick L because it looks like a 1, but you could use an L that's got like a loop. Like that would be okay for a variable. All right. But B equals 2J. Let's finish the definition. It's a two-part definition, right? It's not just that B equals 2J. J's got to be an integer. All right. And so to emphasize that we have literally gotten what I consider proof money, we've got an equation about A, we've got information about K. This is all really good stuff. We're going to spend all of this. We're going to use all of this. If we don't use all this, then something went wrong. All right, let's see how we're going to use it. Well, at this point, it's very helpful to look at our wish and maybe even expound on our wish. This wish is to show A plus B is even. Let's think about what that really is going to look like. All right. So I'm going to say we wish to show. WWTS means we wish to show. I want to expound on this idea. We wish to show A plus B is even, but that means it's going to look like 2 times, I don't know, M. I like M in my thinking notes, where we will be able to say M is in Z. M has to be an integer. See, and when we kind of expound on our wish, it does a couple of things. It tells us, hey, we got to look at A plus B. It also tells us exactly what we're going to need to say about A plus B, okay? In order to really nail the definition of even, because we're trying to prove that sum is even, and that sum looks like this. So here we go. Let's look at A plus B. Observe. I like the word observe. It's just a good way to start a sentence. We can't start a sentence with little a plus b because little a isn't an uppercase letter. Okay, you can't start a sentence with a lowercase variable. So I just stick a word in front of there. So I've got a nice capitalized letter. So a plus b. What is a plus b? Oh, look, we know what a is. A is equal to 2k. We can use substitution. Plus B. Ooh, B is equal to 2J. We can plug that in for B. Now, you see, we have burned this money. We have just spent these two pieces of money. But we're trying to get the 2 on the outside times something that we'll be able to say is an integer. So what should we do at this stage? Just pull the 2 out. Just factor out the 2. And then k plus j is the quantity that we're going to have to talk about being an integer. That's going to be our m, okay? That's going to be the m that's an integer. And now we use the closure properties. We have to verify k plus j is an integer. Why is it an integer? Well, look, k is an integer. That's part of our proof money right there. K is an integer. We got to use that right now. J is an integer. So notice k is an integer and j is an integer. So m equals k plus j is in z. That's just another way to say it's an integer. Because why? Sums of integers are integers. That's one way to say closure. Under addition, you can say sums of integers are integers. We don't have to prove that, but we do need to say that. So now we just kind of wrap it up. A plus B is equal to 2 times m, where m is in z, which means A plus B is even by definition of even. We have nailed the definition of even. We have addressed all parts, namely the 2 parts. A plus B looks like 2 times an expression. And that expression is definitely an integer because it's built from the sum of 2 integers. Questions? So this is our first universal proof. Super simple. It's about as easy as it gets. Here's a do later. So, I mean, the suggestion, of course, is that, you work on these and you come to office hours and talk to me about these. Prove the product of 2 odd integers is always odd. So this will be a chance for you to practice using the definition of odd. And be sure and do good step 1 and good step 2. In other words, be sure and write it as an if-then, introducing variables. That way you can get your eyes on the hypothesis that you get to have to start your proof off, and you can get your eyes on the conclusion that you want to establish using the definitions in algebra. We're keeping it simple. All right, let's do another universal proof now together, just so that we can, get a little more practice under our belt. So another universal proof. Big difference between these universal proofs and the existential proofs, right? With these universal proofs, we've got to use variables and algebra. Example 4. Prove the product of an even integer and any integer is always even. Okay, this is a classic example. And I actually think that this is also a WebAssign problem. So we can, we're working through it here, and that should help you when you work your WebAssign. So we're going to do good step 1 and good step 2, right? Let's write it as an if then. So let's see, how many objects do we have? How many objects are we going to need to have a variable name for?
Two.
Yep. We have an even integer, right? And we have any integer. So we're going to need to name those. So here we go. If I'm just going to use C just for variety. If C is even and N, that's a good letter for just any integer, is any integer, then, all right, you help me. What is the then part here? What is it that we're trying to prove?
Then A times B is always even.
Yeah, and this time I switched it up on you. I'm using C and N, but A and B would have been fine. If you were using that A is even and B is any integer, A, B would work fine. I'm going to say C times N because that's the letters I'm using. But again, use any letters you like. You can use X and Y, doesn't matter. Is even. Okay, so we've got a hypothesis here. We've got that C is even and N is any integer. That's our hypothesis. We have the conclusion here that C times N is even. So we know what we're trying to do. We're trying to assume C is even and N is any integer. And then we're going to do the work to show C times N is even. Here we go. Proof. Always let your reader know where your proof starts, folks. Assume is a really nice word to start off your hypothesis, but that's not the only word you could use. Another word that can be used would be suppose. Some people prefer that. Suppose C is even. Notice I'm not even saying even integer. I'm just saying it's even because we know that evens and odds are integers. So you can get away with just saying C is even. Suppose C is even and N is an integer. That would be one way to write the hypothesis. It's not the only way to write it. It's just one way to write it. You're going to get your own style going. But we definitely need thinking notes. We wish to show Cn is even. We definitely need to know what we're trying to do. All right, so we're going to break out the definition of even as applied to C. By the definition of even, so we tell our reader what we're doing. We're applying the definition of even. By the definition of even, C is equal to 2 times K, where K is NZ. We can reuse K now. This is a new proof. We can use K again. And we might want to take a closer look at our wish. What do we wish to show? Again, these are simple proofs. We're just starting off real easy, that C times N is equal to 2 times M, where M is an integer. We're trying to show that C times N satisfies the definition of even. All right, observe. Here we go. Just a nice way to start a sentence because I can't start a sentence off with the lowercase letter c. We're looking at C times N though. Cn, what do we know? Well, we have this nice, proof money that, when we used the definition of even, we got this good stuff, right? C looks like 2K, so we can plug that in for C right there. Substitution is critical. Times N. But look what we're trying to do. We're trying to make c times n look like 2 times an integer. It's not quite there. What should we do? We can just slide those parentheses over, right? Just regroup. It's called the associativity of multiplication, right? It doesn't matter if we multiply 2 times k first or if we multiply the k times the n first. It's going to turn out to be the same product. So we can do that. And then now, we see, okay, the m that we're hunting for is going to be k times n. That's our m now. So we've got the first part of the definition of even done. We've got Cn equals 2 times something. Now we just have to talk about that something being an integer. That's what I mean. Both parts of the definition of even are important. So let's talk about k times n. Well, notice kn is a product of integers k and n. Just trying to show you a different way to write stuff. So kn is an integer. That's the closure property under multiplication. And now we can just wrap it up. We're there, folks. Thus, c times n equals 2m, where m is actually equal to kn is in z, which makes cn even by the definition of even. All right. So a couple of easy proofs to start us off. And this special homework 5, it's only to do with evens, odds, primes, and composites. All right. By the way, be sure and read section 4.2 thoroughly. Okay, I just want to emphasize that one more time. It's real important. It's going to head you off at the pass before you make some of the kind of classic novice mistakes that you don't want to make. Okay. All right, now we're going to turn our attention to the other side of the coin, okay? We have improving statements, all right? We proved 4 statements so far, 2 existential statements and 2 universal statements. But the other side of the coin is disproving false statements, all right? Because that might be what we're asked to do. We might be asked to disprove a false statement. Sometimes we'll be asked to figure out if a statement is true or false. Prove it if it's true, disprove it if it's false. Let's talk about disproving statements. I want to just show you this basic information. Okay, it's in the notes, but I want to just walk you through it. Disproving statements. Okay, there are 2 things that could happen. We might be asked to disprove a false universal statement. So let's, just like in Tarski, right? If you were trying to prove the original was false, you wound up proving that the negation is true. So to disprove a false universal statement, what do? We prove the existential negation, right? The negation of a universal is existential. We learned that. All of this comes into play. By the way, proving the existential negation is called giving a counterexample. Now, why would it be called giving a counterexample? Well, there's 2 things going on. First of all, we're going to be proving the existential negation. So we're going to be proving that by example. We prove existential statements by example. But why is it called a counterexample? Because what we're doing is we're countering the claim that the universal statement is true. Way back when we started first thinking about if-then statements, here was one that we talked about. If it's a rose, then it's a flower. Okay, that's true. If the object is a rose, then it's a flower. But the converse was, if it's a flower, then it's a rose. That's not true. Now, the reason we talked about that was a different reason. I was just trying to show you the converse doesn't necessarily have the same truth value as the original. But if it's a flower, then it's a rose. We know that that's true, false, because we can give a counterexample. Like it could be a flower and not be a rose. It could be a daffodil, right? Or a tulip. And that's called a counterexample. Countering an if-then with an example that shows why it's false is called a counterexample, okay? Now, perhaps we're going to try to disprove a false existential statement. Well, if that's what we're doing, we have to prove its universal negation, and we can't prove a universal anything by example. When we have to disprove an existential statement, we're actually going to wind up proving its universal statement, its universal negation, excuse me, using variables, equations, et cetera, et cetera. So let's start by disproving a false existential statement, which is going to give us a little bit more practice proving a universal negation. We're going to start with that. So let's disprove. This is our example 5. Disprove this false existential statement. This is the harder thing to do because we have to prove a universal negation. All right, here's the false statement. There exists a positive integer n such that n squared plus 3n plus 2 is prime. All right, so that's a false statement. All right, so the first thing we're going to do is write the negation because we're going to be proving the negation. And the negation is universally quantified. So instead of there exists a positive integer n, it will be for all positive integers n. By the way, folks, just a reminder, when we negate a statement, we don't change the domain. Remember, we've had this discussion. For example, if we're going to negate a statement about dogs, we don't start talking about cats. All right, we're still talking about dogs. So if we're going to negate a statement about a positive integer n, we keep the discussion on positive integers. We don't start talking about negative integers. We're still talking about positive integers. So the negation is for all positive integers n, and then we have to negate the n squared plus 3n plus 2 is prime. So we just say n squared plus 3n plus 2 is not prime. Notice I don't say composite because we haven't figured out quite yet how big this is. It's going to turn out that it's composite, but for sure it's not prime. Okay, and that's the safe thing to do. So we are getting ready to prove a universal statement. So let's do our good step 1 and good step 2, where we write it as an if-then so that we can get our eyes on the hypothesis and conclusion. So here's one way to write it. If n is in Z plus, remember Z plus? That's the set of positive integers. It's been a while, but Z plus starts with 1. Z plus is 1, 2, 3, ... okay? So one way to write this as an if-then would be if n is a positive integer, then n squared plus 3n plus 2 is not prime. That is our if-then formulation, or at least it is one if-then formulation. The nice thing, though, is, hey, now we can see the hypothesis of our proof is going to be super simple. The hypothesis is simply that n is going to be a positive integer. That's all we're going to need. Our conclusion that we're going to try to show is that this quantity, n squared plus 3n plus 2, is not prime. So here we go. Here's our proof. We're going to assume, or you could say suppose, n is a positive integer. N is in Z plus. What do we wish to show? We wish to show n squared plus 3n plus 2 is not prime. So we know we're going to have to either verify that it's too small to be prime or that it factors. And I think you can see right now this is not going to be too small. Because check it out. The smallest that n could be is 1, right? So n squared at its smallest is 1. Plus 3n, well, that's at least plus 3 more, plus 2 more. This is at least as big as 6. All right. So the reason it's going to fail to be prime isn't because it's too small to be prime. It's going to be because it can be factored. And of course, this factors very easily. Observe. N squared plus 3n plus 2 can be factored into two factors, n plus 2 times n plus 1. All right. And this is going to be our A, and this is going to be our B, right? Remember the definition of composite. Let me grab it one more time so that we can look at it. An integer is composite if it looks like A times B, where A and B are integer factors, and both of them are bigger than 1. So here we go. We're going to have to verify that both of these factors are actually integers and that they're both bigger than 1. But that's easy to do because we've got closure. We know n is an integer. And my phone has just died, but that's okay. We are getting real close. So let's just talk about these factors. All right. So notice A equals n plus 2 is an integer, right? Because n is in Z and 2 is in Z, and Z is closed under addition. This is just another way to say sums of integers are integers. I'm just trying to show you a couple of different ways to say stuff. Also, B equals n plus 1 is in Z for the same reason. Same reason, closure under addition. All right, so we've got that n squared plus 3n plus 2 is the product of two integers. Finally, we have to verify that those integers are big enough. Here we go. So finally, 1 is less than A. Why? Because n is bigger than or equal to 1. So A, which is n plus 2, is bigger than or equal to 3. That's definitely going to make A bigger than 1. And 1 is less than B, right? Because B is equal to n plus 1 will be greater than or equal to 2 since n is bigger than or equal to 1. And then you just wrap it up. Thus, n squared plus 3n plus 2 is equal to A times B, where A and B are integers, and 1 is less than A, and 1 is less than B. This makes n squared plus 3n plus 2 a composite number, so it is not prime, and that's what we wanted to prove. So we're really nailing all the parts of the definition of not prime. All right, we've just got like one more minute, and what I want to do is show you one last thing. We're not going to work it, okay? But I do want to just point out to you that there is, more game here, and I'm going to leave it as a do later. It actually appears in the special homework. And here it is. Here, I'm asking you to disprove a false universal statement by giving a counterexample. Remember, when we disprove a false universal statement, we are proving its existential negation, and that is called giving a counterexample. Here's the false universal statement. It's written as an if P then Q. For all integers m and n, if m times n is a perfect square, then m and n are both perfect squares. So here's the P, mn is a perfect square. Here's the Q, m and n are both perfect squares. So there was a reason why you had to learn to negate an if-then. All right, it wasn't just academic. Here's the negation. P happened and Q failed. The quantifiers change because the negation of a universal is an existential. The negation is there exist integers m and n such that P, mn is a perfect square, and not Q. Oh, we have to be able to negate m and n are both perfect squares. Well, we know De Morgan's laws, so we know the negation of that is that m is not a perfect square or n is not a perfect square. It's the inclusive or. You can give an example where they're both not perfect squares. It's not the XOR. So my point is, this is the easier kind of thing to do because we're going to be proving an existential statement by cooking up an m and an n where the product mn is a perfect square and either m or n or both are not perfect squares. And that's actually the last problem on your special homework. And it's this particular problem where I even ask you to figure out if it's a true statement or not. But I've told you here that it's a false statement. So I've kind of given away that much of the problem here. All right, so proving universal statements, can't use an example. Proving existential statements, we can do that by example. Disproving universal, you're proving the existential negation by counterexample. Disproving existential, you're proving the universal negation. There's no special word for that. It's not called like a counter universe. It's not called anything special. It's just a disproof of an existential statement. So let's get back to the gallery, see if we've got any questions, any answers. Okay. We're getting in the thick of it here. Oops, where'd my video go? Oh, it's weird. There it is. Any questions? All right, so those of you who are here, I'm glad that you're here, and welcome to our visitors who dropped in for the video lecture. Anticott and Isaac, I'm glad y'all made it. Hey,
Thank
Anticott.
you. Hey.
Yep. It's convenient sometimes to be able to drop into the online
Yeah.
lecture. All right, folks, listen, there is an office hour at 8. I'm going to be sitting here waiting for anybody to come into the room. If you want to go ahead and take a peek at that special homework, I'll be right here. Of course, we'll also have a nice office hour on Sunday night. If you feel like you just can't stomach more discrete math right now and you need to take a break, I'll be around on Sunday night as well. And I'll be grading your work. Please make sure that you check out your graded work. It's all uploaded there in Blackboard for you. Okay. It was good to see you in person. For those of you who sat with me on Monday night, it was nice to breathe the same air and actually be in the same room together. And for those of you who are at Tune taking that test, I'm glad that that worked out. I got your test papers. I went and got them yesterday morning, and I got my work cut out for me for the weekend, right? I'm going to be grading your papers. I'll try to be gentle. I thought it was an easy test. I didn't try to make it really hard, right? I didn't build you a huge circuit, with like a gazillion AND gates. I tried to make it, basic. I'm hoping people did well. I'm really hoping people did well. I tried not to throw any curveballs at you. All right. I'm going to stop recording, but I'll stick around for a little while in case anybody wants to chat.